Tobin, and today I'll be talking about shufflers. The first question is, what is a shuffler in the big context? In the big context, it's an active interrogation diagnostic. So how does that fit into the full context? You basically have active and passive. As a general rule of thumb, I'd say if passive works, you'll use it. When does it not work? It doesn't work when the material you're interested in doesn't give you enough information, so it's not putting off enough gamma or neutrons to tell you something, or you put something around the material such that you can't get the information that it's putting out well enough. So a shuffler, now it's roughly described active versus passive. Within the scope of active, you have, you can generally say they're different by the energy of which you're interrogating, as well as the size of the object you're interested in. So the most common diagnostics are an active well. Active well, you'd be using M-racing lithium sources. So you're looking at your interrogating sources, something that is just below 1 MeV. And your interrogating source is a part of your diagnostic. You're not moving it around. So those two facts limit you to lower objects. So shuffler, as compared to an active well, has interest because you've gone from the M-racing lithium source up to a Californian source. So your energy has gone from sub 1 MeV to an average of 2 MeV, but you're actually dealing with a spectrum that goes as high as 8 MeV. Then other diagnostics, on the active route, you can go even higher in energy up to a neutron generator, which is something we've been researching lately and putting into a shuffler to take advantage of that higher energy range. So with that background, are there any questions on context? Darn, let's head on into the talk. So the talk basically breaks into three parts. There's shuffler physics, and then I'll do a lot of pictures, examples of shufflers in the field, and then what we've been working on most of the past few years are calculational techniques to calibrate them. So I'll describe how we've traditionally calibrated them, and then what we've been working on to use Monte Carlo. So what does a shuffler do? In the most simple sense, you're determining the mass of a fissile isotope, and that's not totally true. You could also be determining the mass of a fertile isotope. But in general, you're interested in the fissile isotope, 235 and 238, 239, neptunium, well, it's fertile, but and you're doing this, you're determining the mass by detecting delayed neutrons. And where are the delayed neutrons coming from? You use a radioactive source, as I mentioned earlier, californium. You interrogate the material. You induce fissions. From those fissions, you create delayed neutron precursors. It's on the order of 300 to 400 precursors are sitting there after a fission has occurred, and they emit delayed neutrons on time scale of a second out to a minute. And those are what we're detecting. And I just mentioned that the interrogating source is californium, and we're really measuring what's emitted from the daughter products, not actually from the fissile material of interest. So here's a schematic of a shuffler. Half of your shuffler is just a block there to shield neutrons, because this source is very, very strong, on the order of, a typical shuffler has 1/10 to the 9th neutrons per second. The strongest that's ever been made by this group was up at 610 to the 9th neutrons per second. You take that strong source and you pull it into the assay chamber. So while it's in here, you're irradiating the source of interest. You've surrounded the chamber with helium-3 tubes. When you pull it in here, for most intents and purposes, you're not even interested in any of the neutrons. You're not even measuring them. I'll get into a caveat to that later. But in general, you're just irradiating it. You pull it away. You've made essentially no measurement. And it's not here till this moment in time when you've returned your radioactive source up here that you're now interested in what's being emitted from the source. You're interested in delayed neutrons. Here's a cross-section of a shuffler, so cut it in half. You'll see 6 banks are very typical. Most of what I'll be talking about now are what I consider, what's often said is the standard shuffler. Shufflers have been were first developed over 30 years ago, and in the 90s there were a number of labs that were interested in them. So this group wasn't interested in becoming a factory for shufflers. Instead, they licensed the technology, and there's the standard shuffler. There's 6 or 7 of them out there, and this is a cross section of that standard shuffler. So you're looking at the 6 banks here. There's also a bank on top and on bottom. You have a turntable that spins your source around, and this standard shuffler is designed for 55-gallon drums to give you a dimension. And then you have a real lot of shielding. Now the reason you have a very excessive from one sense of shielding is because it's a very strong source. Safety limits require you to shield it. Well, it has the added advantage that is a forte of a shuffler is that you have very low background. All this shielding, although it's there for physical protection of your personnel, it creates a very, very low background environment. And then once again, to compare it to an active well, not only do you not have near this much shielding, but your source is inside the chamber while you're measuring at all times. So that gets an idea of one of the inherent strengths of a shuffler is very high precision. A couple points here. I'm going to point out the banks. The entire shuffler is lined with cadmium. That's to make sure that your goal in the end is to accurately determine the quantity of fissile material. If you didn't have cadmium, you'd be having more neutrons returning from the walls, and it would lower the energy spectrum inside the chamber, and you become more susceptible to self-shielding. So that, put another way, the edge of your grams of uranium on the outside of the material are going to give a stronger signal to those on the inside. You would like for that to be a more uniform response throughout the material. That's why an active well has a context. They run in what they call fast and a slow mode. They take out the cadmium. So they're dealing with the exact same concept. The shuffler could also do the two modes, but you never bother doing that because if you're going to go to a shuffler anyway, you're generally going to want to be in a higher energy range. And the shuffler, you don't have to worry as much about having a real strong source because you're going to pull it away anyway when you measure as compared to the active well. Okay. So I think I've covered everything there. Oh, I didn't mention this one. There are two, I missed these ones. Also, the helium, just to put more context, the California source comes down along this block of iron there for a reflector. I also neglected to mention that we have flux monitors in there. That basically are two helium-3 tubes, one with cadmium around it, one not. The one without cadmium is sensitive to all neutrons. The one with cadmium is basically not seeing the very low energy ones. By taking a ratio of those two, you now have a rough measure of the energy spectrum inside the chamber, independent of the particle flux. And so both tubes are in there at the same time measuring. They're both measuring at the same time. You just take the ratio of them. Now, those flux monitors have been used in some cases to quantitatively make matrix adjustments for your calibrations. As we'll get into further, one of the key challenges for a shuffler is dealing with the fact that your energy spectrum changes depending on the moderator inside the chamber. And that'll significantly change your count rate. So if you can't quantify it, how do you deal with it? What has been done is experimentally using flux monitors. More often they're used just as a qualitative indicator. Okay, so I mentioned this is giving us more detail on the Californium source. Here's its energy spectrum. So it peaks just below 1 MeV. Your average is out a little above 2 MeV, and I mentioned before it goes up to some substantial contribution up at the 8 MeV range. Why do we use Californium? Amazingly small sources can give you a lot of neutrons. So 10 to the 12 neutrons per second per gram. In general, the standard shuffler usually uses around 500 micrograms. They've used as low as 30 micrograms and as high as 3,000 micrograms. This energy spectrum gets you, in general, deep penetration. One of the disadvantages of Californium is you have this 2.6-year half-life. So when you're ordering a shuffler, you don't want to be replacing it that frequently. The rule of thumb is to order your source so that you get 10 years of use out of it. This is the main motivator for putting a neutron generator in a shuffler. The people that are dealing with replacing it and all the bureaucracy involved are quite interested in not having to handle it with a strong source. Even right now, we no longer use the shuffler in this building because the source has gotten so weak. It was just a research shuffler anyway, but it's still the strongest source in the building to give you an idea of the strength of the source. So you have the initial energy spectrum of the emitting source. Then those neutrons go in, and here's the energy spectrum you face after that. What do I say? The energy spectrum you face. The goal is to fission. Your goal is to induce fission. Although a shuffler has been used for a variety of materials and contexts, its workhorse is assaying uranium. So here we see the spectrum of uranium-235. Your neutrons are emitted up here at this energy. Your fission probability is getting higher and higher and higher. 3 orders of magnitude change. In general, for most assaying cases, you're assaying in the 200 to 20 keV range. If you have a very highly moderated case, clearly you're going to shift down to lower energy. And as you can see, this is what I just mentioned earlier. This quantifies the whole issue of how much moderator is inside your diagnostic. If you were to say for gamma technique, what is its Achilles heel? Dealing with attenuation. For a neutron diagnostic, your Achilles heel is dealing with moderator, because you need to know whether you're getting that many fissions or you're getting that many fissions. Since you're often looking at uranium-235, and it comes with 238, you're going to want to know what the characteristic of 238. So 238 has a very sharp cutoff, near 1 MeV. That's one of the strengths of an active well, is that you've chosen your americium lithium source such that that energy being emitted is just below this threshold. You don't have to worry about fissioning 238 directly. You're always going to fission 238 if you're fissioning 235. Just to remind that, because you're going to be fissioning it, and those are in the 2 MeV range, the fission neutrons. So you'll always be doing some fissioning of 238. But to minimize it, a strength of the active well is that they stay below this cutoff. So another key point to mention, although if we overlaid this cross-section of 238 and 235, you'll notice that the 238 is about a factor 2 lower in this 1, 2, 3 MeV range. But bear in mind, in the shuffler we're measuring delayed neutrons, and 238 emits about double the number of delayed neutrons. So effectively, once you get above 1 MeV, 238, 235 give you the same signal in the shuffler. One thing that's been used successfully to deal with this is spectrum tailoring. What do we mean? Basically, if you're putting off that spectrum we looked from californium, and it's bad for you, stick more material between what you're interested in assaying and the radioactive source and cut the energy down. So one thing they have around many of the shufflers is a poly lining that just stacks over a drum, so you can shift your energy spectrum down. You could also build it into the shuffler to just put more iron in front of it, or lead if you wanted to. A variety of materials could be used to cut the energy spectrum down depending on what you want in the end. Okay. So a little more just focusing on the delayed neutrons. So backing up again, we saw the spectrum of californium. Then we saw the spectrum of the material we're fissioning. Now we're describing the next step in the process, is what are the delayed neutrons. So we're describing the delayed neutrons. Roughly 1% of neutrons emitted from a fission are delayed. Specifically for 235, it's fortunately a bit higher, 1.6, but for 239 plutonium, it's down factor of 2.3 lower. These delayed neutrons are coming from, I put more than $300 products. I've also seen it stated as more than 400. So there's a wide variety. You often hear me say just calling them precursors. It's another word. Delayed neutron precursors is the same word as fission fragments that are emitting the neutrons. Back 30-some years ago, when this was first being investigated, Tobin, who did the first work on shufflers, to my knowledge, looked at what was emitted from all these hundreds of daughters and said, you can pretty well reproduce that behavior if you just say they fall into 6 groups. And those 6 groups each have their own unique half-life and their strengths, which are relative strength, which is described here. Here we're looking at 235 and 239, and here are the half-lives. You basically see between the 2 groups, they're really, really close. They're essentially the same. And the strengths, other points, your strongest group is here at, with a half-life of 2.3 seconds. These 2 combined are about equal in strength, so you're in the tens of second range. The weaker groups are the long and the short ones. This is just to give a graphical, taking those half-lives that we just described, the 6 groups, putting it in a shuffler context. In a shuffler, the standard operating procedure is to irradiate on the ballpark of 10 seconds. So what happens to these? I'll get into more detail on standard operations shortly. But just now, having that been said, what happens in 10 seconds? For 10 seconds, you see the buildup of your precursors. So over here I have delayed neutron precursors. Basically, you have your radioactive source in the chamber. It's inducing fissions. You're going to be building up precursors. So they're building up. And here it's done for each of the groups. You begin to see that certain of the groups are saturating. The longer groups clearly aren't, but they're fairly weak. A comment on that one advantage if we do go to a neutron generator is that with a shuffler as we presently run it, half of the delayed neutron precursors you produce during your radiation time decay during the irradiation time. So you're being rather inefficient with your detecting neutrons. Why are we being inefficient? Well, it takes about a second to get the source in and a second to get it out. You're not going to be pulling it out too quick just to not lose those neutrons. If you can cut down on that the time to get in and out, which neutron generator, you're talking turning it on and off, so you're now on a very quick time scale. That's one advantage. You could be basically roughly a factor of 2 more efficient with your neutrons. Also, and during this, if anyone has questions, please do interrupt. Another thing, just a peripheral thing. I remember when I first started doing this, I came from a background that didn't have much. My first thought was, okay, you're irradiating this thing, you're pouring with neutrons. Well, aren't we going to use up to 235? And you do a back of the envelope calculation, and you realize pretty quick that you're nowhere near to that. One way to put it, if you assayed an item 1 million times in a shuffler, you would use up 1/billionth of the 235. So it's not at all a concern. And a similar thing applies to helium-3 tubes, I believe. I actually haven't done the calculation on that. Anyone? How much of a helium-3 tube do you use up? I never heard anyone even being concerned about completing it. Here I go into the timing of a shuffler. Standard operating procedure for a shuffler in the standard shuffler is you open up your doors, you put your 55-gallon drum in there, or more as often you take a small object, put it on a stool in the middle of the shuffler, and you take a 270-second background. It's worth pausing for a second to say what is background to a shuffler. Most people think of your traditional background. Okay, you got things around you that are radioactive. Great. Something that's not considered as background in many measurements is spontaneous fission. Putting it another way, anything that's not a delayed neutron is background. So when you put your item in, you put your item inside the assay chamber to measure your background. So whatever material you're dealing with, you're measuring there. And this is one of the reasons why it's not used for plutonium that much. Plutonium is highly radioactive. You're getting a lot of neutrons. You can use it for it. And conceptually, the strength of the shuffler is, conceptually you have some background level. You could drive any signal you want above it, right? You could bring in, if you're totally being impractical and don't consider the real world of you can only handle so strong a source, you could bring in a source 10 to the 14th, ready to take out something, drive the signal above drive it above whatever background you have. And that strongest source I mentioned was being used for assaying spent fuel because they very, very highly radioactive, a lot of curium. You can drive a signal above it if you want. But that background is going to include that. If you're doing spent fuel, it's going to be that curium primarily. Okay, so I digress there. Now, standard operating procedure for shuffler has been 34 shuffles. Why? They basically said, let's make it 1,000 seconds. Sort of the ballpark time frame. If it's 1,000 seconds, you generally get 34 shuffles in. You spend about a second moving the source from storage into the chamber. Then you spend about 11 seconds moving up and down. What the standard operating procedure has been, bring it into the chamber and stop at the top for a second. Bring it down to the bottom, stop for a second and a half. Bring it back up, stop for a second. Bring it back down, pause for a second and a half. Bring it back up, pause for a second, go out. In the end, you spend a little more than half your time either sitting at the top, sitting at the bottom, and the other half of your time scanning. The goal there being try to spread the neutrons around fairly uniformly in the sample. Why they emphasize top and bottom? Because they found that if you just kept scanning, you were emphasizing the middle. So they wanted to weight the side a bit more. So after you've scanned in the middle, you take a second to pull back. Then you count for about roughly 7 seconds. And here you see that buildup of the delayed neutron precursors, the time it takes for the shuffler to move the source out, then you're counting, and then you're decaying away. The first group's decaying away while the second group is building up. And that concept of the two groups interfering or overlapping is what this graph's about. So what are you actually counting when you're doing a shuffler? During your first count time, it's very obvious. You just count that first 7-second period. During your second count time, you're counting the neutrons from the first group, the second shuffle, but you're also getting some from the previous shuffle. And then on and on. So your 34th shuffle, you're technically getting neutrons that are contributing from all the previous ones. In reality, you'll see that for the first 5 shuffles, things are building up, and you reach close to an equilibrium after about 5 or so shuffles. This is another order of magnitude issue. Every time I'm getting in the habit of doing this, I stop when I get to another order of magnitude and restate what we've said so far. First of all, we have our interrogating spectrum that goes into the sample. That was average 2 MeV. We then hit our material, which varies over 3 orders of magnitude fission probability. Then we have our delayed neutrons that come out. I hadn't mentioned their energy. They're a bit lower, but in the hundreds of keV range is the peak. So they're coming out, and what do they meet? Well, they get slowed down as they reach the poly and the edge of the shuffler, and then their goal is to get to a helium-3 tube. Well, depending on what energy they arrive at the helium-3 tube, you have another 3 orders of magnitude change. So if they're coming in at the end, well, they're in the keV range generally. If you slow them down, depending on how much moderator you've chosen in the edge of the shuffler, generally, because you expect some moderator in your item, the shuffler is said to be under-moderated. So as you put an item in there and you keep putting a bare item with no moderator, you get a certain count rate. As you keep adding poly, you watch your count rate go up and you watch it go down. I just throw this in there to give a ballpark idea of what collisions do. So if you're trying to go from 2 MeV down to thermal, it only takes 27 collisions, optimum collisions, and hydrogen to bring you down. If you're colliding in lead or uranium, it's 1,000. Flux monitor, I don't know if I need to pause there. I pretty well talked about that earlier. Here's a sort of sidetrack to of some rudimentary imaging work that was done by Phil Reinhard. Since moderator is so crucial in a shuffler, you can put an item in there, you get a certain count rate, you can put poly around and you watch it double, triple. Those order of magnitude changes are very significant. You need to be able to handle them. So one way to handle it was to think, well, if you knew where the item was, you'd be much more able, and this is leading up to modeling, you'd be much more able to predict the impact of the moderator. So what Phil did was experimentally say, well, let's just see what we can do. So he put an item in the shuffler, and he would take a drum and he put items at various locations located throughout the shuffler. He put it in there and he'd make a measurement without rotation. Then he'd take the drum and just rotate 60 degrees and make another measurement, rotate 60 degrees and make another measurement. He did that until he'd scanned out all possibilities. And then he said, well, it seems kind of common sense that if an item is here, the bank right next to it is going to get a stronger count. So let's just see if we just make some arbitrary decisions. Say, let's cut the drum into 3 sections, top, middle, bottom. And then let's take each section and break it into 13 parts. Each one of these are equal volumes. And given that, can we get some complicated math along the lines that are used in medical imaging and say, can you localize it under the assumption there's 1 item or 2 items or 3 items? Can you localize it to one of these 30, given the 3 sections, 39 quadrants? And that worked out quite successful. You basically, if under the caveat that you only have 1 or 2 items, it would work out pretty well. You could localize it to one of the 39 quadrants. This is also probably the most important slide of the talk to put a shuffler in context in it, and what is its strength and what's the Achilles heel. And this was leading up in the advanced neutron school. I went into just a few slides of differential diaway. I don't know if you want me to do that here. The reason I wanted to do that is, for one, from past schools, people want to know more about differential diaway. 2, it's only taught in our waste school, and since the shuffler, in certain contexts, the shuffler and the differential diaway system overlap, I wanted to talk about what's the strengths of one and the strengths and weaknesses of both. So what do I have here? I'm talking about neutron penetration as a function of particle size, enrichment, and neutron energy. So there are 2 cases. There's one case which is 10 milligrams of uranium, where it varies between high enriched, 93%, 20%, and 3%. Very small object, so your radius is 0.5 millimeter. And then another object, so much higher mass, 25 grams versus 10 milligrams, so 5 millimeter radius. And then for those 2 cases, let's focus on the first case, so a very small object, and let's look at the fission probability at different locations within it. Where here they're equal volumes once again, where you have the inner volume is, I should say, four separate voxels, basically, of this small object. You see when you're up at, you're dealing with high enriched uranium, and you're interrogating with thermals, you have a factor of 2 variation in the fission probability. That's basically stating that when you're interrogating with thermals, that even for an object this small, the BB with full diameter is a millimeter, you get a factor, you're fissioning twice as many on the exterior than you are the interior. What's happening there is the neutrons, because there's so much 235 highly enriched, you're gobbling up the neutrons on the outside, they're not going to get into the middle. Even though you're 20%, you don't notice much of a difference, and nothing at 3%. If you raise to the average energy of californium, basically you see no weighting with location inside the source. Now move to the larger object. Once again, starting off the thermals, you see several orders of magnitude issues when it's high enriched. The 20% enriched, you get an order of magnitude change. The thermals, you get a non-negligible change. I guess you're going from what? 4 to 6. But when you stay up at the higher energy, even for an object this size, you don't have much of an issue. They're fairly straight lines. So this emphasizes the strength of a shuffler. Basically saying if you keep the energy high, you will. One of the problems is the objects are very large. This gets at the Achilles heel of the differential diaway system, and that I'll get to shortly. So intro to differential diaway. As I mentioned, why discuss it? It's a competing comparable diagnostics. They're both large diagnostics generally, and they can handle 55-gallon drums. What is the strength of a differential diaway system? Very high sensitivity. Where is it getting its high sensitivity? Well, with the shuffler, you're generally throwing away 99% of the neutrons from your induced fission, right? Basically, cause that fission. You don't even count a thing then. Differential diaway is counting that. So that's where it gets that's its strength and its high sensitivity. But its potential weakness is that the self-shielding issue. It's interrogating with essentially thermal neutrons. Now, what's interesting, I remember I first heard about differential diaway, you're getting your neutrons from a DT generator, 14 MeV, so higher energy. And you say you're interrogating with thermal. And that's sort of a mixed statement, which I'll get to in the next slide. Differential diaway must use a neutron generator. A shuffler could use a neutron generator, but up to date it always used California. So, differential diaway. Key thing I'm not standing up here as a differential diaway expert. My goal is to give across the basic ideas. But the key to understanding a differential diaway system is to think in a time domain. So, what happens when you're doing a differential diaway assay? You basically have a burst of neutrons on a tens of microsecond level, and they're coming off of 14 MeV neutrons. Then, you're not going to count any of those after the burst. Why? Because your goal is to learn something about the material you're assaying. In both the shuffler and differential diaway system, you have way more neutrons coming from your interrogating source than you ever have from your the sample of interest. So you need to somehow discern what's coming from your neutron source from what's coming from the material of interest. In a shuffler, we do that by pulling the source away and then counting. In differential diaway, they do it by turning their source off, so essentially taking it away, and then allowing time to determine time and energy to allow you to know what's coming from your material of interest. So you had your burst. Now you wait 800 microseconds while they slow down. And they should have said one backdrop before this is well, here basically. Then from 800 to 2,800 microseconds, you count neutrons with high energy neutron detectors, and that's sort of the key point to a differential diaway. You've designed your detectors by putting boron and cadmium and poly around them, or sometimes using a helium-4 detector, so that your detector is only sensitive to high-energy neutrons. High energy, what does that mean? It means, well, you're interested in fission, neutrons given off directly from the induced fission, and those are generally the 2 MeV range, so you've designed your detectors to detect 2 MeV very well. Well, since that's the only neutrons you're interested in, you start out with 14, you're waiting all this time so that 800 was chosen so that the neutrons, all of them coming from that 14, are so low that they won't be detected by these detectors. In general, you say thermal. I know they try to push it to get a little bit higher than thermal, but it's generally in the thermal range. And actually, I don't know if Mark will say comment, you might know better than I.
There has been some research to go to epithermal, but I think that for most of the DDT systems that are out there, it still is thermal interrogation.
Okay. So that's the key, is understanding that you've waited. So to me, it's sort of it's true and it's false to say that they interrogate with thermal. In one sense, you get the advantage of the initial 14 MeV neutrons, because they're going to go everywhere and penetrate very well, but you're going to wait in time till they've lowered in energy before you start counting. So they do have a higher penetration than if you were actually interrogating from the outside with thermals, but at the same time you're interested in measuring, you are going to have these self-shielding problems of interrogating at a very low energy. Okay, so now that's basically the end of the shuffler's physics. Are there any questions about it? Okay. Next step would be to move on to just pictures of shufflers. This is your standard. First of all, Phil Reinhardt, who worked on this for the decade before I did and was a very good mentor to me and bringing me up to speed. This is a standard shuffler. You have this top half is only there for the Californian source, shielding it, and the bottom half, you open these two doors and put your drum in. An interesting note, if we did go to a neutron generator, one possible advantage is you basically cut your shuffler in half. You no longer need that. So how much will that actually end up being a cheaper diagnostic? I'm not sure, because the generator gets a bit expensive in its own right. Here's an earlier shuffler. Basically, in this case, they shielded the Californian source back here, and there was the assay chamber. It was an ideal assay case. This is the shuffler that got the best results in terms of accuracy and precision. It was sub 1%, probably 0.2% accuracy. And the reason it was an ideal assay situation. You're assaying your fillet. It was also an extremely weak source. It was only 30 micrograms. You can bring the source actually directly to the middle of it, highly enriched, it has those signals. Here's a novel shuffler. It's when you think of a shuffler, one thing I'm trying to get again. I spent the whole first part of the talk talking about the standard shuffler, and then now I'd like to broaden your perspective to some of the other ways shuffling has been done. Here you prepare a sample in a glove box, send it down here. This is lead shielding, and shuffle the source in and out in here. So it's a very small sample. I'll also take a pause for a second here to talk about an even more novel shuffling concept. Is shufflers have been used with liquid material. So in this case, you don't have to shuffle the radioactive source. You just on one part of the pipe put your Californian source and just wait downstream and let the material do the moving. This was a novel shuffler in the sense that it became a barrier between secured area and outside. Basically, drums would go in. They're measured. If they passed me the very low level of radioactive material, they would go out. If not, they brought it back in. Here's a picture of where shufflers are in the U.S. I'll point out particularly where these standard ones are. So here at Los Alamos, we have two standard ones, one at CMR, one at TA55. One out at Livermore is identical. Two in Portsmouth that are not being used. Then they'd like to, but they can't get strong sources of them yet. Y12 has one. Savannah River has a number. Oddly enough, they don't have a standard shuffler, though. Dunray, Scotland has some. The French have some. Maybe make a comment on the French one because it was rather novel. Phil did some collaborative work with the French to compare our technique and theirs. They basically did the assay much different than we did. Their goal was, our goal is we call it an integration approach. They say, how many delayed neutrons do we count from for 7 seconds? We just count neutrons. They would try to shoot their source in real fast, shoot with a pneumatic gun, so high air pressure, and then just try to detect the decay rate, to do a decay curve. From that, extrapolate to what strength the signal had at t equals 0, and determine it from that. I'm not sure the details of their analysis, but it was, rather than doing an integration, they were doing a curve shape. Turned out that the techniques, in the end, are identical. Our technique turned out to be more precise, but in a shuffler, precision is already a strength. What limits you, what you really have is accuracy. What limits you in accuracy is how well you do the calibration. And since that was basically the same in both cases, the results were identical. Okay, now to talk a bit more about calibration. If we were to talk about 10 years ago about shufflers and calibration, we'd essentially have stopped at the red line, because that's what was done. You basically would go, if you had a shuffler, you would go out and buy shuffler standards, or you'd make standards that fit your assay needs. So you take your 10 standards, you stick it inside your shuffler, you get this nice curve, and then you put an item in there that is close to your standards, get some count rate, and then match it up and say you have that much 235. Okay. Works great if your standards and your unknown match in chemical form, shape, density, all the things that don't match. So you need, and as I went through earlier, I was trying to emphasize these orders of magnitude change in fission spectrum with energy, the variation in the UM3 detection with energy, all that to get it. Energy is very important, so you need to quantify it. So moderator needs to be handled. So if you are going to differ from your standards, if your density, if your enrichment goes up or your density changes, those are going to change what's valid, what your calibration curve should be. We just made a comment on a couple of them. If you go to higher density of, let's see here, we're talking about moderator. If you're more dense moderator, your neutrons aren't getting in, therefore your count rate's going to go down for the given amount of 235. If your enrichment goes, remember this graph is by 235, if you basically say you're going to low enrichment, another way of saying that is you're staking in 238. Sticking in 238, you now have another source of delayed neutrons. So if it's low enriched, you generally go above the curve, because 238 is contributing. So all these factors are important. They all change the count rate. If you can't quantify them, you're just stuck with accepting them as biased. Monte Carlo is where I'm leading with this, and where I've actually, this is 90% of what I've done as I've been hired as the shuffler guy, is to use modeling to quantify these effects. Here's data to actually show you it. You basically have a metal standard on top of that same your U308 oxide standard. So this oxide standard is in the 2.5 grams per centimeter cubed density. In metal, you're talking about the 19 grams per centimeter cubed. So you see the effect of the metal drop lower calibration curve. That's blowing up the same metal curve, so you can see the difference again. And here you're seeing some of the enrichment effects. As you go to low enrichment, and the 238 is contributing more, it bumps up the count rate. Back to this. So this emphasizes the main point that what caused all these variations are sample matrix, shape, density of the chemical form, enrichment. All those things need to be quantified. And how do you extend it? Using modeling. And what does modeling stand on? It really is, we always say the word modeling. What it really means is someone has gone through and understood the physics of every step along this process. And we feel we know that physics well enough that we can put it into a code. And if I'll show you the results Phil has produced with modeling shufflers, that physics holds up very well. So here are Phil's results. He basically took the standards and modeled them. He used 4 different objects to basically look. There are two types of objects that you'll see. Let me back up. What we're looking at here is, my point in this slide, I'm jumping ahead of myself, is to show that the modeling and the calculations work well. And there's a big caveat to this that I'll get to at the end. You'll see here you can't even really discern the calculated source from the measure. So here's over a large range up to 8 kilograms, and here's down at the up to 1 kilogram. Great result. The huge caveat though is, or if anyone here has experienced with buying Californian sources, they would say, how can you even get results that good when you don't even know the strength of your Californian? You go out to the manufacturer and buy it, and they often will give it to you. And I've heard varying ranges of 10% uncertainty. How can you even do anything if you don't really know your source strength? So the huge caveat is, well, how did we determine our source strength? Well, you take the same standards that he's comparing here, and you put them in the shuffler, and you measure all of them. And he took more than just these standards. He took metal pucks in a wide variety. So he used metals, he used oxide standards, and I'll show you results shortly for weapon pits. He basically put all those things in there, and so he just used the metal pucks and the oxide to determine the source strength. Put them all in there and measures them, and then calculates what he should get. And when in the calculation, he leaves one variable unknown, source strength. And he basically says, after he's done all the modeling, what source strength would make all my measured results and my knowns match up. And so once he's done that, then he gets this. Now, first thing you hear, they think, gee, that's cheap. It just doesn't seem right. But once again, it's not right if your goal was to calculate count rates from a first principles perspective. It's all right if your goal is to accurately assay uranium-235, because you have any biases that are involved, and there are biases. My expectation, I've redone these. I'll go into a little bit later that the calculation techniques Phil used and the one I'm using are different. MCMT has evolved in the late 1999, 2000. They put in the ability to delay neutrons direct. Phil used a technique where he broke the problem into many models and put all the physics together inside an Excel spreadsheet. Now the way MCMP works is you can do all the physics inside the model, inside MCMP, and in the end you just multiply it simply by count source strength. Boom, you're done. So it's taking all the physics in MCMP versus all the physics in Excel spreadsheet. I expect to get a different source strength because Phil has to make more assumptions than I have to. The new code does the physics more accurately. So why do I get a different source strength? I mean, I'll get a different source strength for the exact same measurements he did, using the exact same data, because there are biases built into this technique. We call it the source strength, but in reality, if you haven't put in your moderator quite right, if you haven't included, like the moderator of the shuffler, you haven't totally designed it right. For example, Phil, one error he made is 2 of the banks. In the course of putting this new technique in, I had to put all kinds of fine lines. I noticed that 2 of his banks were not, the location helium 3 tubes were not correct. Inside the doors, they drifted, and they drifted on the order of a centimeter. So on one end, you'd have 1 centimeter, 2 centimeters of poly between you and the helium 3 tube. On there, 2.5. That's pretty significant when you talk about helium 3 tubes and moderators. But it didn't make it. He still got these great results. Why? The bias induced with that was built into every measurement he made, every model he did. So yes, it's a bad thing to have in there. It's been taken out, but it didn't reduce his results, his ability to get very good agreement, because that bias was the same for when he did his standards and when he did his unknown. So. So that was a really long excursion, and to the point of saying the ability to measure and calculate is quite good, but underlying that is that you've spent the effort to determine your source strength. And when I talked to statisticians, they wanted me to back down from using the word source strength because of some of the effects they just talked about. We started calling it a fudge factor. This is our fudge factor because it has biases built in. Here's what Phil I mentioned also did weapons fit. So if I remember correctly, he used the metal pucks and the oxide standards to determine his fudge factor source strength. Then he took something in, it was a vastly different object, weapons pits, with uranium and plutonium in them. So weapons pits are not very much like oxide standards or metal pucks. So a very different geometry, and also adding plutonium, so you're getting a much higher background. And he did 9 different pits and 5 different types. And the worst he did was slightly under 4% at predicting their mass. So a very good test of this concept of using the fudge factor. How am I doing on time? Just keep going? All right, some miscellaneous things that are like stream of constants I covered. Calculations are altering the role of standards. There's a question of how many standards do you need. And why are we trying to find a way? I feel like part of my goal is to end the need for standards. It's not really to end the need, but to definitely limit it. Speed standards are multiple hundreds of thousands and millions of dollars. If you've gone now, Phil for a shuffler has gone and shown great results. What's the difference between now sticking neptunium in there? What's really changed? Most of all the uncertainties are already covered. They're inside the shuffler model. Now, the only thing you've changed now is your nuclear data. So now the added uncertainty is only at the level of your nuclear data. Okay. And flat out, there are some cases where there just are no standards. You have some esoteric type materials that you're not going to want to go out and spend tons of money to make the standards. Caveats with the calculational technique: it's easy to get up here and sell how great it is, and it all comes down to it's great if you know everything, it's perfect. Well, if you knew everything, why would you be doing it? But know everything really means you know your hydrogen. So you could be it's fine to have the new. We saw if you don't know how much uranium is in there, great, that's not a problem. The collisions in the uranium aren't going to matter. It's really knowing hydrogen. So if you know how much poly is in there or any other moderators, then you can. The unknowns in the other materials generally are negligible. And the other caveat being you need to spend the effort into getting to know your source strength or fudge factor very well. Precision and accuracy. I've alluded to this. Shuffler is known for its precision. You get very, very, very easily get high precision by the fact that you can choose how strong your signal is by your source strength and your very low background, depending on what choose to put in there. When you put curium in there, it starts to get higher. But in general, precision is the forte of the shuffler. Accuracy depends on how well you can do your calibration. When would you use a shuffler? So why do people go and buy them? Shufflers are rather expensive, so when do you use them? As I've been emphasizing, 235 is one of the primary things, but in general, when it's large, if an active well will do your job, you should use an active well. It's smaller, cheaper, more portable. But for those cases where you have larger objects or you need greater energy penetration, a shuffler will work for you. It's worked for mixtures of uranium and plutonium, and I haven't actually gone into detail on this yet. Let me take a moment for that. What you generally do is do a two-step measurement. You do either in a shuffler can act as a coincidence counter, try to quantify the plutonium. If you happen to have a better diagnostic, higher efficiency diagnostic, you may want to quantify your plutonium in a multiplicity counter, and then go to a shuffler, where now you're going to do a normal assay like I said, except now you're going to determine your delayed neutrons from combined uranium and plutonium, and you're going to subtract out how many of those delayed neutrons came from the plutonium, because you already measured that, you already know it, and now you're going to say you know how many come from the uranium, and you're going to use that. Now clearly when you do a two-step process, your uncertainty goes up. Another issue that happens is, since you have plutonium in there, you're generally going to change your count rate to better quantify your background. And Livermore has done UMPU, and so is the standard in a shuffler. I've mentioned a couple times that we can do fissile material in the press, and so high spent fuel context. And then also just emphasize that you get high precision and a relatively short count time is another reason people want a shuffler. Situations that challenge a shuffler, number one is the poorly characterized matrix, so when you don't know how much poly is in there or moderator. High spontaneous fission rates are going to limit you. Conceptually, I said you can always override it, but realistically you're not going to be able to get as strong a source as you need in all cases. Also put a tight budget. It's up among one of the most expensive diagnostics that there is. And I think I'll hold off on going into neutron generators. I alluded to them a few times. Summary. Hopefully you got the point that we're measuring delayed neutrons. 30 years of experience in the DOE complex. Very precise diagnostic accuracy depending on calibration. And Monte Carlo modeling is changing the way calibrations are done. So that would be it. Any questions? Shuffler never grides, that's the goal. Great, thank you.